Just one more time, let's reiterate what the p-value is. The p-value is the chances of getting the sample statistic that we got if the population parameter we assume to be true is true. So let me just make that clear. So he's saying, look, if this is really 0.5, if this was really 50% like you claimed it was, what are the chances of getting 5% for our sample? So you can say, okay, well, that chance is really small, less than 0.0001. Minitab actually finds it to be 4.1397 e negative 16. Okay, really, 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 really small. That's the chances of you getting that far away from what we expected, from getting 5%, when if it was really 50%, like you said, the chances of getting 5% or less by accident, by random fluke, is that small. That's what the p-value stands for. And if it's small enough, you're going to reject your null hypothesis. You're saying, look, you said that it was 50%, but if it was 50%, there's no way, well, almost no way, we should have gotten 5%, which is what we actually had for our sample p hat. Okay? So when you find the p-value, that's what you're finding, the probability of getting what you got by random chance. If it's low enough, then you know something is up, and you go, nope. That null hypothesis must not be true anymore. It's got to be something else. And again, we have assumed through all of this that we have a random sample, it's independent, it's unbiased, that n times p times 1 minus p is greater than 10, and all that jazz. We have to assume all of that, at least at this point. If you were going to go to another class after this one, we would start dealing with what happens if those assumptions fail. But we're not working with that. All right. So that's what we were talking about right here. The p-value is the probability of the p-hat being what it was by random chance. Now, keep that in mind as we answer these questions. If you have a p-value of 0.03, is that a significant result at the 0.05 level? Okay, now when they say this, that 0.05 level business, what they're talking about is alpha is 0.05, right? 0.05 level of significance, okay? By the way, this is true. Okay, why? Well, because your p-value, 0.03, is less than 0.05. If you have a lower chance of happening than your threshold, you're saying, look, my threshold for garbage is the 0.05 level. So if my p-value is lower than that, I'm rejecting the null hypothesis. That's it. That's all. That's what the p-value is. That's why I love the p-value method. It's so simple. If your p-value is low, you reject. Done. Right? So if your alpha is 0.05, which they're saying it is, and your p-value is 0.03, then you will reject, and that is statistically significant. Right? If it was p-value of 0.02, right? A p-value of 0.02 provides more evidence against the null hypothesis than a p-value of 3. That is absolutely true. Lower p-values are more evidence against your null hypothesis. I mean, look how low ours was for our example. It was crazy low, right? 4 e to the negative 10. That's 0.00000000004. Really, 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 really low. All right? So therefore, we are going to say that that gives us more evidence. Don't forget that statistical significance is tied up with rejecting the null hypothesis. Okay, so when they say, is it statistically significant, what that's code for is, do you reject the null hypothesis, right? Reject the null hypothesis is the same thing as statistical significance. So if we reject the null hypothesis because our low p-values are low, that means that it's statistically significant. So a p-value of 0.02, or I should say p-value equal to 0.02 will cause us to reject the null hypothesis more often than a p-value of 0.03. For example, suppose alpha was 0.025. If alpha was 0.025, we would reject when the p-value is equal to 0.02, but we would not reject when it's equal to 0.03. Which means that automatically a p-value of equal to 0.02 is stronger than a p-value of equal to 0.03, right? Gives more evidence. In other words, look, if your threshold for getting rid of the null hypothesis is being less than alpha, then the lower your p-value is, the more significant it is, because the more you're going to be rejecting, period. All right? Okay. So if your p-value is less than alpha, that is statistically significant. Don't forget that statistically significant means reject the null hypothesis. Okay? All right. And then the lower your p-value is, the more evidence you're getting, the more significant that's going to be. I don't know if we'll have time to do this next problem in this video, but let's get started and see how it goes. So we have the National Transportation Safety Board published statistics on the number of automobile crashes that people in various age groups have. Young people aged 18 to 24 have an accident rate of 12%, meaning that on average, 12 out of every 100 young drivers per year has an accident. A researcher decides to test these results and gathers a random sample of young adults and finds out whether they had an accident in the last year. The hypothesis test outputs for 2 computer programs are below. Right, so this is the kind of thing that, so like on a final exam, say, you won't be doing so much with all this other stuff, you know, maybe a classical method by hand or something. But what you could do is I could give you the computer output and say, go to town, right? Do the methods. Matter of fact, I could have you do both p-value and classical method from this information, because there's enough in these outputs, in either one of these outputs, to give you enough to do either method. Okay, so I could give you enough info that you can fill the rest of it out yourself, right? And that's totally a good use of my test-taking time on the final exam or on your third exams or whatever if you're in a face-to-face class. So these are really important questions. And you can see I've already circled some things here. So what parameter is being tested? So if you look up here for both of them, you can see P, proportion, P, right? It says proportion right there. So P, that's the one that's being tested. What type of test did this researcher perform? Well, you can see the greater than symbol for the alternative here or here. And again, you don't know which output you're going to be looking at, so make sure you know how to read both of them. Because I might throw Minitab at you, I might throw StatCrunch at you, you never know. I could throw something else like an SPSS output. See how you wing it. All right, so this was a right-tailed. And we noted it in each output right there. All right, now state the null and alternative hypotheses in symbol form. Well, you can see it's right there. P is equal to 0.2, P is greater than 0.2. Both of them say that, right? P is equal to 0.2. This particular program uses HA, H-A, alternative. A stands for alternative. This one doesn't even bother writing it. It just, you know that the first one's the null because it's got equals, and the other one's the alternative. All right, how many young drivers did the researchers survey? Well, N was equal to 1,000. So that's how many, right? It says it right there. And right here, the total is 1,000. Okay, so let's go down. How many young drivers had an accident? I'm going to make this disappear for a sec. In the last year. That was 134. That's X, right? I don't know if you want to call it this, but it's a success, right? Because for us, remember, success and failure from binomial, it doesn't always mean a good thing. So for us, having an accident is counting as success. So that's 134. All right, what was p hat? Well, they tell it to you, 0.134 right there, but you can figure it out for yourself even if it wasn't given with a simple calculation. 134 over 1,000 makes 0.134. Now, let's find the test statistic. That's Z0. That's step 3, right? So Z0 is 1.36. It's right here, 1.36. Right there. Boom. All right. The p-value. P-value is 0.087. So right there, 0.087. 0.087. They're very kind and just tell you p-value, right? The probability of getting what you got. So let's perform step 4 of the p-value method. And again, I don't have to break it down like this. I could have just given you these outputs and said, perform the test, which means you'd sit there and type step 1, step 2, and so on. All right. So here we go. I put down the 1.36. That's my Z0. I draw a curve, 1.36. My p-value is over here. It's 0.08691 or 0.087. And so you label it. So there you go. There's step 4. You draw a picture. Yes, you have to draw the picture when you're taking paper and pencil tests. You sit there and draw the normal curve and shade it. If the researcher set alpha to be 0.05, would these results be statistically significant? All right. I think the answer is no. I wrote yes there, but I think this is a big fat no. So no. Because the p-value is greater than 0.05, so we would not, not reject H naught. I think I was full of it, right? So if I set that at 0.05, my p-value is bigger than that, so no. I mean, my chance of getting what I got is only 8.7%, so that's pretty high. And again, remember that statistically significant, I put it up here, but statistically significant equals rejecting the null hypothesis, right? Equals rejecting the null hypothesis. That's what they mean when they say that. All right. Okay, if the researcher set alpha to be 0.05, what conclusion would we reach? There is not enough evidence to support the claim that young people have an accident rate that's higher than 12%, right? Because our sample data was only 1.36, right? I know it was high. Our proportion was 13.4%. So 13.4% of young kids were having accidents, teenagers were having accidents, but that's not high enough to warrant calling out the guard and getting rid of the 12%. Because when we say it's 12%, what we really mean is it's around 12%. So this 13.4% is around it. It's only 1.36 standard deviations above. That's not unusual enough, so we're not going to reject the null hypothesis. There's not enough evidence to support that claim that more than 12% of kids have accidents, or young drivers have accidents. All right, we are all done with 10.2. I hope you enjoyed your first foray into hypothesis testing. We'll be back here for 10.3, which guess what? Hey, look at that. More hypothesis testing. All right, I'll see you then.